Welcome back. This is Food on Wheels problem part 2. Hopefully you had a successful part 1. As we usually do, please pause this video, go through the problem statement, identify all relevant elements, and then return to us in a few minutes so that we can continue working through it together. Good luck with that. In this part 2 of the Food on Wheels problem, the company tries to implement a different strategy. So we no longer have the 2 kitchens, but we're talking now about one central kitchen. So remember what we talked about the provided data. In this case, we don't have anymore all the capacity constraints for the 2 kitchens since those 2 kitchens do not exist anymore as part of my model. From the central kitchen, we're going to send the boxes to 3 distribution hubs by motorbike, which makes no difference here because they only deliver 1 box at a time, just like the bikes. And then from the 3 distribution hubs to the city areas. As you know, our objective function will still aim to minimize time, but minimizing time will include now an inbound time and an outbound time considering the hubs. To do so, we used to multiply minutes and flows in boxes per day. Now we're going to do the exact same thing, but we need the minutes from the central kitchen to each one of the hubs and from each one of the hubs to each one of the areas. So that's the information we're provided, the minutes between those. And we also have a capacity in boxes, but now this is for the hubs. So it's time to go to question 1. And as we have talked, you already know we will have an objective function. We already have the demand constraint set from the previous part of the problem that has not changed. And we also have a capacity constraint, but this is not the same we had in the previous part of the problem. So it's a slightly different. We're now talking about the hub capacity and not about the kitchen capacity, but still a capacity constraint. We of course still use the non-negativity constraint, but the new element here, whenever you have a transshipment point that is not aiming to become a warehouse for your products, is to have a conservation of flow constraint. This is going to force the model so that anything that goes inside the distribution hubs also flows outside of it, because we cannot and we don't intend to keep any units in there. So anything flowing in should be also flowing out, and that's what the conservation of flow constraint is going to do. I encourage you to submit your answer, double check the show answer button, and of course use the forum for further questions. And then let's go together to work on our spreadsheet so that we identify the minimum total delivery time in minutes per day for this new adjusted distribution network. My favorite recommendation and the way to go when moving from one part of an optimization problem to the other is to never overwrite your model or adjust your model in the same tab of the spreadsheet, but duplicate it so that if you want to go back, if you want to analyze and compare results, if you want to see if you made any mistakes, or if at any point some problem statements tell you, okay, now we disregarded that new policy or that new strategy or that new model, and we want to go back to the original one, then you don't have to need it all over. This is also very, very helpful to debug your model. So let's do it together. I'm going to just duplicate my tab, creating a copy at the end. And I will just rename this as part 2, and we'll start from there. Some of the information we have received in the past has changed. We still have the demand in boxes, but now we don't have 2 kitchens and 1 area, but 1 kitchen and 3 hubs. So let's bring that information with us. I'm going to delete everything I don't need. And this is hub 1, 2, and 3. Okay, so that's the information I'm bringing. I used to have capacity in boxes here for the kitchens, but now we can use this place for the capacity of each one of the distribution halves. So this is 150, this is 100, and this is another 150, sorry. And I'm going to do some color coding, you know that, we love it. And this was gray here. The next element I want to add is the delivery time from the distribution halves to the city areas in minutes. So that's also new information. This is the outbound, as we talked. And we can just bring our titles here. And I think with that, we have all the information from the problem statement. I'll maximize my spreadsheet view so that you can follow along with me as we start adjusting our variables arrays and fixing our objective function before going to the solver parameters. Okay, so given information that we have and we are good to go is of course the demand and also the minutes, inbound and outbound. So I will just call this inbound and this outbound so that you can clearly identify what I'm talking about. And then we need to replicate, as we did in the past, the variables using both tables in this case. So I'm going to have the inbound probably here for the variables. Just going to make this yellow, you know that. And then I'm going to fix this one so that I include halves instead of kitchens. I'm just copy pasting this. I'm just using this matrix so that I don't have to do it all over, but you can definitely just copy paste above it. I'll just delete all numbers. So double check all your calculated fields, and this is what we have talked about before. The flow to areas before was only considering 2 kitchens originally in this same table. Now I'm talking about 3 halves. So I need to be sure that I'm summing up all the flow from all halves to all areas for this. In this one, as we already have 5 areas, we should be good to go. I'm just going to place everything together so that it's easier for you to follow along with me. So now we have the inbound and the outbound here. And we need to add some calculated fields, and we also need to add some changes into our objective function. The first thing I want to do, and I recommend doing, is calculating separately your inbound and your outbound transportation time instead of just doing one objective function holding both. This is easier for you to better understand how your model is behaving, to better understand your outcomes. Just imagine that in the future something changes and you want to explore what was impacted, whether the inbound or the outbound. It's going to be much easier if you already have that information clearly identified on your model. So what I'm going to do here is add a couple of rows and just make it inbound time and outbound time. Okay? So these are going to be calculated fields for me, not the objective function. And the objective function at the end of the day is going to be just the summation of both, right? Inbound and outbound. Okay, so how do we calculate the inbound? Just as we talked before, this is just a sum product of the minutes to go from the central kitchens to each one of the halves, time the units flowing from that same central kitchen to those same halves. So this is going to be just a sum product of these 2 arrays. Okay? Great. The next is going to be the outbound time. We're going to do the same, just considering the 2 arrays that have the information from hubs to areas. Okay, what I encourage you to do right now is to give it a try, adding one data point into the variable place, so to see if your formulas are working properly. And Again, in this case, this is a very simple model, but you want to be able to test your model. So anytime you're working with any size of information, just try to have a way so that you can identify whether everything works well even before running your solver. In this case, I'm going to add, for example, 10 units flowing from hub 2 to area 2, and I just want to see if that's replicated into my outbound time properly. So I will click enter, and you can see that hub 2 to area 2 has 10 units. 10 units times 4 minutes means that I have an outbound time of 40 minutes. So that's showing that the model is doing the correct calculation when it comes to the objective function. You can do the same with changing anything into the inbound part. So I'm doing hub 3 in central kitchen, 10 units. You can see it's doing 10 times 7, giving me a 70 inbound time. You can also see that this is replicating here in the transportation time. So anytime I touch this, it's going to add both and just give me the final transportation time for the entire network. With that, I think I'm ready to go. We do have the calculated field for the hubs. So we have the total number of units flowing from each hub to compare with the capacity. We have the flow to areas in terms of comparing with the demand. And we also have how many units flow to each one of the hubs to compare how many units go out of those, so that we use the conservation of flow constraint. So I'm going to go to data once again and solver. And you can see here that the objective is still set. And D1 has not actually changed, even though the formula within the transportation time has affected my objective function. It's still located in the same position. So for the solver parameter, it's still on D1. We're still minimizing, so that's not changing. But we now have two sets of variables, as you can see here in yellow. So I'm going to just delete the original one and be sure to add both variables arrays. Next, I had the non-negativity constraint that was only considering a piece of my table, so I'm going to just delete that and have it all set again. So all my outbound flow should be larger or equal to 0. And now let's add that my inbound flow should always also be larger or equal to 0. Let's go back and see what else we had in here. We also had that the flow out of each one of the hubs, and we need to adjust this wording I had here, should be lower or equal to the capacity. So now we need to fix that to include all the flows from all hubs, lower or equal to all the capacities from all hubs. Okay. And then last but not least, we had the demand constraint. We still have the same position for those. So again, every total number of units flowing to each one of the areas should be the same or more of what they demand. You can see that that has not changed, so I will just click OK. And it seems we already have all our constraints from the previous part adjusted to the new model, but now we're missing the conservation of flow constraint. So this one is going to say that any number of units flowing in should be exact same, because in here we need to leave no units to any units going out of the hubs. Okay? With that, we're going to just run the model, click solve, and see how it goes. I encourage you to populate your answers within the questions coming in part 2. Let me know how it goes, and please analyze your results. If you want to know more of the kind of insights we gather from the results, stay to the last video of this recitation for more details on that. And I encourage you to start doing it also in the discussion forum together with our CTAs and our outstanding community of learners. Go for it, and see you in part 3.